Good evening. Welcome to the presentation of our work on learning long-term invariant features for vision-based localization. This has been a collaboration between Video Computing Group, UC Riverside, and Electronic Research Laboratory, Volkswagen. So in a vision-based localization solution attempts to provide the alternative or supplemental solution to the GPS-based solutions. In a vision-based solutions, we usually have a data set of location-coupled images, and when a new image comes, we try to match that new image with the database images and guess the location. The challenges of this task are many. Like the same location will look very different over the time. Maybe you will come from a different viewpoint, and there are dynamic things like person and vehicles. Also, definitely over the time, over the seasons, it will change a lot. And it's not possible to always develop new data sets again and again. So the existing approaches are mostly based on hand-engineered features, and the recent ones are using pre-trained features. But unfortunately, these features fail to satisfy the requirements of environmental invariance. And now to develop a feature which has such environmental invariance, it's very tricky because developing a physics-based model is not possible because the complete space of transformation between images taken at the same location at a different time are unknown and likely non-uniform because it's generated by nature. So in this work, our focus is to generate a learning-based method which will generate a feature descriptor suitable for the identification, identifying same location at different times by discovering the invariant patterns in the scene as well as the models of how the patterns change over time. So we pose this problem in terms of denoising autoencoder. In a standard setting, a denoising autoencoder takes the input, generate the noisy version by a predefined corruption process, and autoencoder tries to reconstruct back the original sample from the noisy version. In our case, we considered that an image at a place is a noisy version of the other image at the same place. And there are some unknown stochastic mapping exists between these natural image pairs, but we don't need an explicit corruption model. The nature is generating both noisy version and the original version for us. And the resulting system, when we train with these pairs, it will learn the features which are discriminative for this task and also invariant to this environmental changes. Now this is the overview of the system. In a training phase, I have told about that we are training denoising autoencoder using natural image pairs as a source of supervision. Due to high complexity of changes between scenes, instead of directly using images as input, we are using deep CNN feature extracted from the pairs as the input to the autoencoder. In the testing phase, using our feature extractor, we are extracting feature and generating some initial matches by matching the images in database. After I get some initial matches, these location candidates are further analyzed to get the match with the highest temporal consistency. We evaluate this method on 5 different datasets. The first 2 datasets was used in training along with the different time-lapse images. The last 3 was used only in testing. For performance measure, we use F measure. Our result is on the right side of the table. You see that we consistently achieve better performance than pre-trained CNN features like LXNet, VGG16, and VGG19. Also, a place recognition-based feature NetVLAD, and a baseline system in visual recognition sequential SLAM. Similar result also we see from CMC curve in different ranks, where our results are showed in the red. We consistently achieve different performance better than other methods in different ranks. So these results confirms 2 key premise of our work, that the pre-trained CNN-based features may be suboptimal for this task because they're not tailored for this task. And using our method, we can generate a feature which is better suitable for this task, which will assign lower importance to potentially confusing features, and it will learn invariance to illumination and other global changes. Thank you all for listening. Please visit our poster for more details.